Welcome to another lecture on vector calculus. Today I'm going to be talking about the tangent and normal vectors. So in particular, I'll start out with the unit tangent vector. The unit tangent vector is really important, and it has a lot to do with the tangent line to a curve. It'll work in any dimensions, and it's specifically designed for vector valued functions. Then after that, I'll define the principal unit normal vector. That also is a critically important vector, and it helps us understand not necessarily where we're going, but it's perpendicular to that. And then after that, we'll look into acceleration. And in particularly, with acceleration, we will look at the tangent and normal components of acceleration for a vector valued function. And then finally, we'll have an application. We'll take a look at how to navigate a spaceship. So as that goes, let's start out with the unit tangent vector. So the definition of the unit tangent vector is as follows. Let r of t represent a smooth curve C. Then the unit tangent vector t of t, capital T of little t, is defined as follows. Capital T of little t, the unit tangent vector, is equal to r prime of t over the magnitude of r prime of t. Now remember that r prime of t is also called the velocity vector. The derivative of the position is the velocity. So we can look at t of t as being the velocity vector divided by the magnitude of the velocity vector. Dividing by a r prime of t and magnitude makes it a unit vector, and that's why we call it a unit tangent vector. Also notice that if r prime of t is the zero vector, this can't be defined because then you get 0 divided by 0, and that's never good in math. So we only define the unit tangent vector when r prime of t is non-zero. So now let's look at an example. Find a unit tangent vector for general t and also at t equal 2 for the curve defined by the vector valued function r of t is equal to t cubed minus 5 times I plus 4t squared times j. So we go to our formula, and in the formula we need to find r prime of t. Well, this is pretty easy in this case because we just have polynomials. The derivative of t cubed minus 5 is just 3t squared. So we get 3t squared times I, and the derivative of 4t squared is just 8t. So plus 8tj. And that is r prime of t. Next, we need to find the magnitude of r prime of t. So to do that, we take the square root of the sum of the squares of the components of r prime of t. 3t squared quantity squared is 9t to the fourth, and 8t quantity squared is 64t squared. We take the square root of all that. So now we just put this all together to find the unit tangent vector. So remember, the unit tangent vector, t of t, is equal to r prime of t divided by the magnitude of r prime of t. So that's 3t squared over the square root of 9t to the fourth plus 64t squared I, and then plus 8t over the same square root, the square root of 9t to the fourth plus 64t squared times j. So that's t of t for any general t. To find the unit tangent vector when t is equal to 2, we just plug in 2. Very simple. So 2 squared is 4, 4 times 3 is 12. There's my 12. 2 to the fourth is 16. 16 times 9 is 144. 2 squared is 4 times 64 is 256. So we get 12 over the square root of 144 plus 256i. and then 8 times 2 is 16, divided by that same square root of 144 plus 256j. And then we simplify. 144 plus 256 is 400. Square root of 400 is 20. 12 over 20 is 3/5. So we get 3/5 I. And similarly, 16 over 20 is 4/5. So plus 4/5 j. And there is the unit tangent vector for this vector-valued function evaluated at t equals 2. So let's look at a little bit of geometry. Again, it's nice to be able to do a little calculus, throw in some algebra, plug in some numbers, but it's good to have pictures too. So let's suppose we have a function. So here is a vector-valued function, r of t equals t e to the ti plus 2t plus cosine t, quantity j. And there's our curve. So we can look at the tangent line to this curve, and then we could look at the unit tangent vector at that point on the curve. And as we can see, the unit tangent vector is always parallel to the tangent line to that curve. So in particular, if you want to find the equation of a tangent line to a curve, or just the equation of a line, you need a point and you need a parallel vector. Well, the point is easy. You just plug in your t and you get your point, because a vector is equivalent to a point. And the parallel vector is the unit tangent vector. So now let's apply this. We have r of 0. Let's plug in. If you plug in 0, you get 0 e to the 0I, which is just 0I, plus 2 times 0 plus cosine of 0. That's 0 plus 1, which is 1. And you just get 1j. I'm writing it in pointy bracket notation, a little bit less writing on the board. So we get 0, 1 as a vector for r of 0. R prime of 0. So to do that, we just use the product rule here. And the product rule, we get e to the t plus t times e to the t. If you plug in 0, we get e to the 0 plus 0, which is just 1. So there's our 1. And for the next one, we have derivative of 2t is 2. The derivative of the cosine of t is negative the sine of t. If you plug in 0, you get 2 plus negative the sine of 0, which is just 2. So there's our 1, 2, or I plus 2j, however you want to write it. So now we can write down what the unit tangent vector is. So the first thing, note that the magnitude of r prime of 0 is the square root of 1 squared plus 2 squared. 1 squared plus 2 squared is 1 plus 4 is 5. So it's the square root of 5. So I just divide r prime of 0 by root 5, and I get 1 over root 5, 2 over root 5. So now let's put all this together and find the equation of the tangent line to this curve defined by the vector-valued function r of t. And I'm going to write the equation first as a vector-valued function itself. So to do that, if you remember, we have a line. And when you have a line, you take the point, which is 0, 1, and you add the parallel vector times t. So we get 0 plus t times 1 over root 5, just 1 over root 5t for the I component. And then we get 1 plus 2 over root 5t for the j component. I can also write this in parametric form. And we could say x of t is 1 over root 5 times t. And y of t is equal to 1 plus 2 over root 5 times t. And that's the parametric equations to the tangent line to this curve defined by this vector-valued function r of t at the value t equals 0. So now let's talk about the principal unit normal vector. And for now, we're staying in 2 dimensions. We'll move to 3 dimensions in a bit. It's a little easier to write it in 2 dimensions and definitely easier to draw pictures. So let's continue on to the example we had before. Notice that we had our vector-valued function. We have our tangent line, and we had our tangent vector t at the value t equals 0. And what we want to do is we want to find a unit normal vector. So that means we want to find a unit vector that is orthogonal to the vector capital T, to the tangent vector. So one conundrum we have is that there are always two vectors that are tangent to a specified vector in the xy plane. So the principal unit normal vector will be defined as the unique vector that is perpendicular to the unit tangent vector that goes into the curve. So notice the curve wraps around this n of 0. So we want to find the unit normal vector that goes into the curve, and that's called the principal unit normal vector. So just a little bit of calculus first. We can say, this is clear, but you have to think about it a bit. 0 is equal to the derivative of 1. That should be clear to all of you. But t, capital T, the unit tangent vector, is a unit vector, which means that it has magnitude 1 for any value of little t. So that tells us that if we dot t with t, capital T with capital T, you get the constant 1. So we can say that 1 is actually t dot t. So we could say 0 equals 1 prime equals t dot t prime. And now when you take a derivative of a dot product of two vectors, we can use the product rule. So the product rule says this is equal to t prime dot t plus t dot t prime. But the dot product is commutative. So we could say t prime dot t is the same as t dot t prime. And then we can combine like terms and say this is equal to 2 times t dot t prime. Okay, now let's take a look what we just found. What this says, especially dividing by 2, is that t dot t prime is always equal to 0. Remember, the dot product of two vectors is equal to 0 means that the two vectors are orthogonal. So that tells you t prime is orthogonal to capital T. Now t prime, even though t is a unit vector, t prime may not be a unit vector. So we're going to define the normal vector, n of t, equal to t prime of t divided by the magnitude of t prime of t. So to find the normal vector, the principal unit normal vector, we take the derivative of the unit tangent vector, and then we divide by its magnitude. Okay, one issue with this is that capital T of t is a little messy. So remember, that's defined by r prime of t divided by the magnitude of r prime of t. The magnitude is the square root of sum of squares. So we're talking about a quotient rule because we have division. Then we have a messy chain rule because of square root of sum of squares, and that could be awful. If you happen to be in 2 dimensions, there is a shortcut to find the unit normal vector, the principal unit normal vector, in R2. So remember, the normal vector is orthogonal to t. So after having calculated the unit tangent vector, and if we happen to know what the graph looks like, then we can do the following. We can note that when you have a vector a comma b, ai plus bj, then you can find an orthogonal vector by switching the components and making one negative. So notice that if we take a dot product of a comma b with b comma negative a, you get ab minus ab, which is 0. Now, you can make the other one negative if you want to. So if we take the dot product of a comma b with negative b comma a, you get negative ab plus ab, and that's also 0. So there's always going to be two choices, and we knew that. So the way you decide is you sketch a little picture, and you look at the normal vector that should be pointing into the curve, and then you choose the one that is correct. So for example, if the normal vector is pointing to the left, you make sure that the I component is negative. And had the normal vector been pointing to the right instead, then you make sure that the I component is positive. So let's look at this example. And the example is, find the unit normal vector for r of t equals ti plus t squared j at point 2, 4. And this is the picture of that. You may remember that if you have x of t is t and y of t is t squared, then that tells you that y equals x squared is a curve, and you better know how to graph y equals x squared. That's just a parabola. So this is the picture. And at the point 2, 4, we can definitely see what the tangent vector should look like and what the normal vector should look like. So let's find these. So to find these, we take r prime of t. R prime of t, the derivative of t is 1, so we just get I. And the derivative of t squared is 2t, so we go plus 2tj. And now we're supposed to plug in 2, 4. Now, what that really means is we want to find the t so that you get 2, 4. So here, the easiest is we have ti is supposed to be 2i, so t is 2. You could also say t squared j is 4j, so 2 does work. Notice that. Negative 2 would work too, but then you wouldn't get t being 2 for the I component. So that means that t is equal to 2, and because of that, 2 times t is 2 times 2 is 4, and r prime of t will be I plus 4j. Okay, so there it is in a picture. So now what we want to do is we want to find the tangent vector. So to do that, we take the magnitude of I plus 4j. So we take the square root of 1 squared plus 4 squared, which is the square root of 1 plus 16, or the square root of 17. So I just divide, and I get 1 over root 17i plus 4 over root 17j. And that is the unit tangent vector when t is equal to 2. So now we look and try to find the unit normal vector. So again, we could sit there and find t of t and use the quotient rule and the chain rule and have a huge mess and work it out. But let's do it the easy way. So to do it the easy way, what we can do is we can say that the normal vector points to the left here. So that means the I component of the normal vector is negative. So we're going to switch 1 over root 17 and 4 over root 17, but make the I component negative. And we can conclude that the unit normal vector at t equals 2 for this vector-valued function r of t equals ti plus t squared j is equal to negative 4 over root 17i plus 1 over root 17j. And that's the easy way of finding the unit normal vector. So what happens in 3 dimensions? So we do the same thing, except we can't use a shortcut. So here's the question I have, and that is find the unit tangent vector at pi over 3, that's t of pi over 3, and the unit normal vector at pi over 3 for the vector-valued function r of t equal cosine of ti plus 3tj plus sine of tk. Now you may recognize this from before. This happens to be a helix. Because notice we have a cosine of t and a sine t for 2 of the parameters, and a linear function for the third. So that means it's a helix, but instead of going upwards and spiraling, it goes along the y-axis or around the y-axis in spirals. You don't have to know this to do this problem, but it's kind of cool. So let's go find out the derivatives. So r prime of t, the derivative of the cosine of t is negative sine of t. So I have negative sine of ti. The derivative of 3t is 3, so plus 3j. And the derivative of sine of t is cosine of t, so plus cosine tk. If we take the magnitude, let's work that out. Notice that in the magnitude, we get a sine squared of t plus cosine squared of t, and that's just 1. And then we have plus 3 squared, so we get 1 plus 9, which is 10, and then the magnitude gets a square root, so the magnitude of r prime of t is the square root of 10. So now we could write down what t of t is. So t of t will be negative sine of t over root 10 I plus 3 over root 10 j plus cosine of t over root 10 k. I just divided r prime of t by root 10. Okay, now let's find the unit normal vector. So to find the unit normal vector, I need t prime of t. So let's go get that. The derivative of negative sine of t over root 10 is just going to be negative cosine of t over root 10. Root 10 is a constant, so that helps us a lot. We don't have to use the quotient rule, the chain rule, and any of that. In some cases, not this example, but other examples, be ready for some messy calculus. But this is a nice simple one. So we have negative cosine of t over root 10i. Now 3 over root 10 is a constant. There's no t there, so its derivative is 0, so there is no j component. And then the derivative of cosine t over root 10 is negative sine of t over root 10. So I get minus sine of t over root 10 k. Now comes a little simplifying trick. What we want is the unit normal vector. Now the unit normal vector is a unit vector in the direction of the derivative of the unit tangent vector. So if we multiply by a positive constant, we don't change the direction. So we can just look at this and say, let's multiply by the square root of 10 for both of these. And when you do that, you get negative cosine of ti minus sine of t k. That is not the derivative of the unit tangent vector, but it's in the same direction, and that's all we care about. So it's a little simplifying trick that helps out so that we don't have to do quite as much messy stuff. And then we get even luckier, because if we take the magnitude of this vector, negative cosine ti minus sine tk, you get cosine squared plus sine squared is 1. The square root of 1 is 1. So this is a unit vector. So now all we have to do is plug in pi over 3. When you plug in pi over 3, the cosine of pi over 3 is a half, so we get negative 1/2 I. And the sine of pi over 3 is root 3 over 2, so you get minus root 3 over 2 k. Now that is a unit vector, so that is the principal unit normal vector to this vector-valued function, r of t, at t equals pi over 3. So this is a little involved, but it just follows a recipe. And the recipe is take the derivative of r, take the magnitude of that derivative, divide r prime by the magnitude of r prime, plug in your value, and that gives you your t of that value. Then you don't plug in the value, take the derivative of what you got when you divided, and that gives you t prime of t. And then if you find a simplifying step, do it. Otherwise, just plug in. And if you plug in your value, make a unit vector out of it, and that will give you the unit normal vector at that point. Okay, the next thing I want to talk about is what's called the tangent and normal components of acceleration. So picture yourself going down a mountain road in a car. Okay, now I'm going to give you a nightmare. You're going down the mountain road, and your brakes died. Hit the brakes, nothing happens. So then think about what the car is going to do. So what's going to happen is you're going to do two things. One is you're going to look at your speedometer, and it's going to start speeding up. So we can say that you're going to accelerate in terms of going in the direction of the tangent vector, and that's the speeding up of the car. But then, because you're a good driver, you're not going to fly off the cliff. You're going to hug onto the road, and you're going to go around that curve and hopefully live through it. And when you go around that curve, there's another form of acceleration. That's the acceleration of changing directions. So let's talk about acceleration, and we're going to look at the equation for acceleration and talk about why it can be looked at as two pieces. Remember, the acceleration vector is the second derivative of the position vector, which is r prime, all quantity prime. And then I'm going to do a little trick. We know that t of t is equal to r prime over the magnitude of r prime. So that means that r prime is equal to the magnitude of r prime times t. So the acceleration is equal to the magnitude of r prime times t, all prime. Now I can use the product rule for derivatives of vector valued functions and say that's the derivative of the first, which is the magnitude of r prime, all primed, times the second, which is t, plus the magnitude of r prime, that's the first, times the derivative of the second, that's t prime. And now we can notice something. First is that we can call r prime and magnitude prime. We can say that is the component of the acceleration in the direction of the tangent vector t. So we can say that's, let's call it a sub t. So we get a is equal to a sub t, t. Now t prime is always in the direction of the normal vector. So the magnitude of r prime times t prime is a scalar times the vector t prime, which is a scalar times a vector in the direction of n, which will be a vector in the direction of n. So we can say any vector in the direction of n is going to be some constant times n. So we can conclude that the acceleration is equal to a constant times the unit tangent vector plus a constant times the unit normal vector. And notice I didn't write the dimensions. This could be 2 dimensions or 3 dimensions or more if you felt like it. It just always works. So let's give some definitions. We're going to call this a sub t, the tangential component of acceleration. And we're going to call a sub n the normal component of acceleration. A sub n in physics is often called the centripetal acceleration. You may have heard that. That tells you how you accelerate as you move around a curve, how much you're changing directions, whereas a sub t is how much you're speeding up. And those are the two types of acceleration, and then combined, they give you the total acceleration. So let's get some formulas for these. So I'm going to derive a formula, or a bunch of formulas for a sub t, and I'm going to let you play around with a sub n. I'm going to show you the formulas and let you see that they're true. So let's start out with a sub t. So we know a sub t is equal to a dot t. If you remember, that's how you define a constant like that. If you have a unit vector and you take another vector and dot it with the unit vector, that gives you the magnitude of the projection of that vector in the direction of the unit vector. So that's where that a dot t comes from. And then a dot t is t dot a. Hopefully you know that. That's the commutative property of the dot product. And then t was r prime over the magnitude of r prime. So we still have dot a. Then we could put this all in the numerator, and we could write this as equal to r prime dot a over the magnitude of r prime. And then finally, r prime is the velocity vector, if you remember. So we could say that the tangential acceleration of a vector valued function is equal to the dot product of its velocity vector and its acceleration vector divided by the magnitude of the velocity, which is sometimes called speed. Now for the normal vector, I'm going to let you play with that one. I'm going to read it out, but I'll let you derive it. And that is a sub n is equal to a dot n. That's the same reason why a sub t was a dot t. The next step is a little bit deep, so you can fool around with it, see if you can come up with it. That's equal to the magnitude of r prime times the magnitude of t prime. Now that also is equal to the magnitude of r prime cross r double prime divided by the magnitude of r prime. That's also equal to the square root of the square of the magnitude of r double prime minus a sub t squared. And that will give us formulas that will help us in finding a sub t and a sub n. And which one do you use? Use whichever is easiest. So let's look at an example. So let's suppose we have this spaceship that's kind of flying through space, and the path of the spaceship is given by the vector valued function r of t is equal to 2ti plus cosine of tj minus tk. Let's find the tangential and normal components of the acceleration. So we can start by finding the velocity, which is the derivative of the position. So r prime of t, derivative of 2t, is 2, so we get 2i. Derivative of the cosine of t is negative sine of t, so we get minus sine of tj. And the derivative of negative t is negative 1, so we get minus k. The magnitude of the velocity vector is going to be the square root of 2 squared plus 1 squared, so that's the square root of 5, plus the sine squared of t. So our acceleration vector, by definition, is the second derivative of the position vector, and the derivative of 2 is 0. The derivative of negative sine of t is negative the cosine of t, so we get 0i minus cosine of tj. And then the derivative of negative 1 is also 0, so we only get a j component. So we could say that r double prime of t is equal to negative the cosine of t times j. So now let's work out the rest. So to find a sub t, I'm going to use this formula that says that that's equal to v dot a over the magnitude of v. So v was 2i minus sine of tj minus k, and if we dot that with negative cosine of tj, that's a, then that tells you the I and k parts zero out, and all we're left with is negative sine of t times negative cosine of t, which is just sine of t times the cosine of t, and there's our dot product. Then we're supposed to divide by the magnitude of v. So the magnitude of v was just the square root of 5 plus the sine squared of t. So there we have it. The tangential acceleration is equal to sine of t cosine of t divided by the square root of 5 plus the sine squared of t. So now let's work on the normal component of acceleration, the centripetal acceleration. So I'm going to use the formula a sub n is equal to the magnitude of v cross a over the magnitude of v. I'm using these because we have v and a, so it makes it a little bit easier. So now let's work these out. To take the cross product, I write down a little matrix ijk, And then our v had a 2, a negative sine of t, and a negative 1. That's the next row. And then the a had a 0, negative cosine of t, and 0. So to take that cross product, we take the determinant of that matrix and take its magnitude. And let's work this out. Notice that the I component is going to be 0 minus a minus a minus. That's negative cosine of t. So we get negative cosine of t I. And then for the j component, we just get 0 minus 0. So there's no j component. And for the k component, we get 2 times negative cosine of t minus 0 times negative sine of t, or just minus 2 cosine t k. So now we're supposed to find the magnitude. So to find the magnitude, we take negative cosine of t quantity squared. That's just cosine squared of t. And then we have plus negative 2 cosine t quantity squared. So that gives us a plus 4 cosine squared of t. So we have cosine squared of t plus 4 cosine squared of t. And that's 5 cosine squared of t. Now we take its magnitude, which means we're taking the square root of that. So you get root 5 times the cosine of t. So we can put this together. And we can say that the normal component of the acceleration, or the centripetal acceleration, is root 5 times the cosine of t over the square root of 5 plus sine squared of t. Just note this works when t is in the first quadrant. If the cosine of t is negative, you need absolute values. I simplified things, we're just assuming it's in the first quadrant. And that's it. We've now found both the tangential components of acceleration and the normal components of acceleration. That's really all I have for you today. Hopefully, you could follow this and understand the unit tangent vector, the unit normal vector, how to make calculations of both of those, and how to separate acceleration into its components as a sub t times t plus a sub n times n. So if you have any questions, please let me know. Or if you have another instructor, please let your instructor know, and I'm sure your other instructor will be happy to help you out. So have a great evening, a great morning, a great day, a great week and weekend, whatever it is for you. But thanks a lot for watching this video.